On to manometers. So a manometer, right, it says it's comprised of a bulb containing a gas and a U-shaped tube. So basically what happens is a manometer is a way of testing the gas pressure inside of an enclosed container, and you use the atmospheric pressure to help you figure out what that pressure is. So in here we have a confined gas. It's hooked up to this U-shaped tube, and so the gas in here causes the same gas pressure, and it pushes down on this mercury in here. And the mercury then can move back and forth from side to side depending on what the pressure is, and you can figure out what the atmospheric pressure is because the pressure of the gas is pushing here and the atmosphere is pushing here. And the difference between them causes a height in millimeters of mercury. And so you can figure out the gas pressure by the difference in height and knowing one of those pressures. So, with our manometer, right, depending on the pressure of the contained gas, the mercury shifts. So in this case, if this gas pressure is pushing down on this mercury and it's higher over here, that means that the weight of this mercury, right, that the pressure that this mercury applies is equal to the difference in pressure. And so because the tube is filled, that means that the atmospheric pressure over here is smaller than the pressure from the gas. So the difference between the heights of the mercury on each side of the tube is a measure of the difference in pressure of the gas compared to the atmospheric pressure. Right, so let's say I knew that this atmospheric pressure was, let's say, 760 millimeters of mercury, and I knew that this height here was, let's say, 30 millimeters. Well, this gas pressure is pushing down harder than the atmospheric pressure. That means that this pressure is 760 plus the 30, or 790 millimeters of mercury is the pressure of the gas in that container. So in this picture here, right, you can see that when the gas pressure is greater than the atmospheric pressure, the mercury is pushed down towards the open end. Is pushed up towards the open end. So that one is here, right? The gas pressure is greater. So this pushes down more, causes the mercury to shift over to the side, and the pressure that column of mercury, right, because of the two different heights, the pressure that column of mercury just through here supplies is the difference in air pressure. And then on the other side, if the atmospheric pressure was greater, then it would push down more and it would rise on the other side. And now this column of mercury is equal to how much less the gas pressure is. So remember over here I said, well, let's say the atmospheric pressure is 760 and the difference in height is 30. Well, because this gas pressure is more, I would do 760 plus 30 and get, okay, well, that pressure is 790. Well, in the other one, let's say this atmospheric pressure is still 760 and the difference in height is still 30, but now because it's lower on the atmospheric pressure side, I know that that pressure is greater. So what's the pressure in this container? It has to be less than the atmospheric pressure. So now I subtract the 30 and I get, well, the pressure in that container is only 730, right? So you kind of have to think a little bit. Which pressure is greater? Is the pressure in the container greater, or is the atmospheric pressure greater? And then add or subtract the height based off of whether you want that pressure to be higher or lower, right? Then I knew that this pressure was higher, so I added it to make sure that the pressure in the container, 790, is greater than the 760. Or, because I know the atmospheric pressure is greater here, I subtracted the 30, getting that this pressure is smaller, 730 is smaller than 760. So you are going to have to think a little bit while you're doing these problems. Okay, we'll keep moving on here. So here's just another example, right? This one says that if the mercury levels are equal on both sides, the gas pressure is equal to the atmospheric pressure, or what there could be is there could be a hole in here, right? There could be a leak, and because there's a leak, then this gas pressure isn't going to be actually confined in there. Sorry. And both this container, because of the leak, would be the same as the atmospheric pressure. That would be one way that they're the same. Or it can be like this one, right? That this side is lower, meaning this pressure is greater than this pressure because the mercury is shifted over. And then you've got the other example, right, where now this pressure is greater than this one because whatever side is further down basically has the greater pressure. So here's an example. It says that gas pressure is greater, you must add the two. So if this atmospheric pressure, let's say, was 760, the standard, and then the difference in height here was that 44 millimeters, then you know this gas pressure is greater, and so you're going to add them together and get 804. And sometimes they'll do the reverse. Sometimes they'll tell you, okay, well, this is 804, and we want to know what's the atmospheric pressure. Well, if you think of it that way, if this pressure is 804, and because it's down further, you know it's greater, then you would have to subtract the 44 to get the 760 that the atmosphere was in the first place. So you really have to think about which one is greater and which one is smaller, and then try to figure out whether you add them together or subtract them based off of that. Here's another example, right? If the atmospheric pressure, we're still just going with the standard atmospheric pressure of 760. If in this case now this pressure is going to be greater than this pressure because it's lower over here on the side open to the atmosphere. So if I want to find the pressure in the gas, I know it's less than the atmospheric pressure. So if the atmospheric pressure is 760, how do I get less than 760? I subtract the height in there, right? Where over here, I knew that the gas pressure in this container was more than the atmosphere, so I knew to add the 44 because I had to get a number that was larger than 760. If they refer to anything as STP, right, it stands for standard temperature and pressure. Well, the standard temperature is 273 Kelvin or 0 degrees Celsius, and the standard pressure is 1 atm or all those values that go to it, right? We had 1 atm, 760 millimeters of mercury, 760 torr, 101,300, and I can't remember. What was that, pascals, or 101 point, maybe it was 325, 101.325 kilopascals and 14.70 pounds per inch squared. All of those are the standard pressures, they're just written in different units, so that's why they're those different values. The last, we already did 2 examples of these, you already did them hopefully, but if you didn't, right, you should be able to go through and do these conversions. So let's see here. We have 456 millimeters of mercury, and we want that to cancel, so that has to go on the bottom. And we want to get to pascals, so that goes on the top, right? And then if you look back in your notes to see what all of those values are that are equal to each other, you find that 760 goes with millimeters of mercury, and pascals was 101,325. Our units of mercury cancels, and so when you get your calculator, right, because that 101,325 is on top, you do 456 times 101,325 divided by the bottom, 760, and you would get 60795 pascals. But because this is 3 sig figs, we would want to do 60,000 or 608. No, what is it? It's hard to read here. 60800, so 60,800 pascals, right? That would be our 3 sig figs. Our last example, 324.3 kilopascals, right? We want those units to cancel, so kilopascals goes on the bottom. We want to get to ATM, so that goes on top. Looking at our conversions, 1 ATM equals 101.325 kilopascals. So you would do 324.3 divided by 101.325, and you would get this huge number, well, not huge number, but a lot of decimals, right? That's what my calculator says, but I want 4 sig figs, so it'd be 3.20. This 5 rounds that 0 up to a 1, so 3.201 ATMs would be our equivalent pressure in ATMs that equals the same pressure as 324.3 kilopascals. And that is the end of our notes for this. At this point, we'll do those last couple parts of the notes tomorrow.